All right. Hey everyone. Yeah, let's get back to work, I guess. So if you remember last time, we were messing around with graph theory. So let's just review quickly. So a graph is generally something that has a set of vertices and has a set of edges. Can I tell you about the final? Sure, I guess. So yeah, the final exam. Yeah, it should be the same format, relatively. So, okay, let's think about it for a second. What should the final exam for this class be, and what should it cover? Well, I guess it can basically be comprehensive. Which means that it should have a unit on set theory. It should have a unit on maybe a little bit of probability, and maybe a little bit of counting. And then maybe an induction problem or two. So yeah, I mean, if there's like 10, let's say that there's maybe 10 problems. Man, goes from wanting me to tell you what's on it to immediately wanting a practice test. Yeah, I might give you a practice test if I have time. There's a lot of things to be done, unfortunately, and not enough time to do even half of them. So I will try to get that out. So when is the final exam going to be? I guess the question is, I don't even know. What was the date for the final exam for this class? I should check. I never actually bothered to look it up because coronavirus kind of messed everything up. So the last day of classes is going to be Wednesday next, or I guess it's actually Tuesday next week. So the 12th. I think I can probably just release the final exam on the 13th, maybe? Wednesday the 13th. And you can have like 1 week to do it. I don't think I'm going to make it any longer. It's going to be maybe 10 problems. Probably something on the order of 2 to 3 on sets, maybe 4 to 5 on probability. 1 to 2, 1 to 2, something like that. So maybe something like this. Does that add up vaguely to, let's see what this adds up to. 6, 7, 8. So that's 8 if we go with the lower end. It's 12 total if you go with that. So I don't know, maybe I'll say like, I don't want to, maybe I'll just say that there's exactly 2 induction problems and then something like this. Oh, well, happy birthday. I'll try to make... You know, I might put one, like a graph theory, maybe extra credit problem or something. Graph theory is kind of hard, so I don't know. That's just what I'm thinking. What else am I thinking? Graph theory, but also maybe say a big O problem. So I might actually only give you 1 to 2 set theory problems, something like this. So on Wednesday we'll talk about big O. Something like this. I haven't written it yet, obviously, so I don't know. Okay. Uh-oh. Okay, whatever that was, I'm going to ignore it. All right. Okay. I mean, so the thing about it is, in terms of how much is there still left, I would say probably not much. I mean, maybe we'll do like a day on big O, and then we'll do, so Wednesday we'll do big O, and then Monday we'll do review. Yeah, Dr. Johnson is going to join in a few minutes, which is good because none of this would have interested him at all. So, all right. So, yeah, I think that's probably right. Yeah, so the final exam is probably going to be, I guess the only thing to really learn from this is that it's probably going to be probability heavy, and the rest of it is kind of just kind of a division amongst the other stuff. How is exam 2? It's going along extremely slowly and painfully. I'm going to try to have so in terms of exam 2, I have I'm going to grade them by Wednesday. Are you going to get a homework or a practice exam? Well, Kevin, I said I'd probably try to get a practice exam out, but oh, how are they looking so far? The 4 I've graded are pretty good. So 4 good. The rest are haven't even looked. So yeah, I'll try to write up the exam answers for exam 2 or something like that. I'll try to get the grades to you by Wednesday. It's let me tell you, it is extremely difficult to use Blackboard to grade things. So I will say that it is taking me a huge, it is adding an inefficiency that is like expanding the amount of time that it takes to grade an exam by like a factor of like 4, right? So unfortunately it makes me feel really inefficient, and I just don't get a lot done. So I've been kind of like trying to figure out a more efficient way to do it, but I think the right answer is just to, after class is done here, just to start grading, and then not to stop grading until either I die of exhaustion or they are complete. Okay. Yeah, I wish that some robot could grade it for me. That would be beautiful. Okay, so let's get back to graph theory a little bit. Yeah, I think maybe, how do you guys feel about a graph theory extra credit problem? I'm kind of liking that. Well, you see, I have a grader who's supposed to grade homeworks, but not exams for this class. So technically, I'm supposed to grade them. Yeah. So, it'd be wonderful if I could distribute this work. Okay. I mean, graph theory is kind of impossible, and I'm not sure exactly what I'd give you. Maybe I'd have to give you like tons of hints and tons of stuff to do it. Kevin wants to grade. Good. Okay. Well, Kevin, you know, so here's a question, Kevin. Would you be mad at me if everybody got an A? Because I suspect you might. You don't like when people get extensions. Just curious. Okay. Also, it's good to see you. Where have you been? Anyway, let's get back to graph theory, because it's definitely the most interesting thing that I've talked about all semester. So, yeah, let's talk about it. So what is a graph? A graph is really just two sets, right? One of those sets is a set of vertices. Sometimes you'll see them called nodes in computer science. And the other one is called the set of edges. This is a capital gamma. I mean, you can also just write G like this if you want, but you know, it's always nice. It's always nice to hit it with a nice gamma. So anyway, you can basically have a graph that does almost anything. Like this is just a fine graph. There's nothing wrong with it. Even this, right? So a graph with some loops on it. This is a legal graph. If you want to get rid of loops, then that is completely a fair thing to say, because a lot of times the problem with loops is that the way that edges are defined most of the time is that an edge is usually defined as a pair xy. So the thing about an edge is that if it's defined as a pair edge xy, I guess you could define a pair as xx. But then if something had two loops, then it'd be hard to tell the two different, like if this was loop 1 and this was loop 2, it'd be a little difficult to tell them apart. So for the most part, I don't want to discuss any loops on graphs for now. Just assume that a graph doesn't have any loops. Assume that it's just some vertices, and each edge has to go uniquely between, say, two distinct vertices, right? The other thing to say is that sometimes you might see some intersections like this right here. And so because there's no vertex there, there's no intersection. All right, cool. So if you remember last time, we were talking about an Euler circuit for a graph. So that's basically a way that you can traverse around a graph so that you can, for instance, like this graph will have an Euler circuit because it's a simple enough thing. This graph, let's see, will this have an Euler circuit? No, because there's there's odd degree vertices. But this graph will have an Euler circuit again. So what is an Euler circuit? Yeah, exactly. So even if all the even degree, or if all the vertices have even degree, so what was degree again? Degree is the number of edges that are incident to that vertex. So here, for instance, this vertex has 1, 2, 3, 4. So it has degree 4. This one is 1, 2, 1, 2, 3, 4, 1, 2, 1, 2, and 1, 2. And so you see that this satisfies the theorem. So let's try to come up with something that had an Euler circuit for this. So let's say that we start here and we go this way, and then we go this way, and then we have a bunch of choices. So we have to see every vertex. We have to we have to go along every edge. So basically we can do something like this. And this is an Euler circuit if you trace this around. You'll end up back at the starting point. So this was the start. It's also the end. That is really confusing me. Okay. So anyway, so this is an Euler circuit. And basically the requirements for an Euler circuit is that a graph has an Euler circuit if every vertex has positive degree. And so if you remember, the proof of it was actually pretty, what should I say, intuitive. Well, I should just read what I have right here. It was pretty intuitive. And the reason why it was intuitive was because basically whenever you're at a vertex and you have a whole bunch of edges coming in, right? Every time you enter that vertex along one path, you have to leave that vertex. So let me just draw it in blue. So every time you enter a vertex, you have to leave that vertex. You enter, you leave, you enter, and then you leave. Or I guess leave and then enter is how I drew it. So the point is that they all have to pair. And because all of the vertices, or all of the edges have to pair, like an enter pair with a leave, then what ends up happening is that there has to be an even degree, because there has to be an even number of things around here. And that's exactly what this proof says here. It basically says that you just count the number of edges and you say, well, okay, if there was an odd number of edges, then it would be impossible to have an Euler circuit. Basically, it's the contrapositive that we're really proving, I guess, or what I'm really talking about in a sense, right? The contrapositive says that if there exists an odd degree vertex, then there is not an Euler circuit. Right, so if a graph has an Euler circuit, then every vertex is positive even degree. And so what's the negation of having positive even degree? Well, that means that there exists some odd degree vertex, and if there's an odd degree vertex, then there's not an Euler circuit. So that's essentially the contrapositive there. So the next thing I want to talk about, and this is just like a random smattering of graph theory. I think it's kind of interesting. Yeah, so at an Euler circuit, you can't get stuck at any particular node, because if you had, as I say, if you have three edges coming into one node, then at some point you have to come either in or out on this one. Say you go out on this one, and then you come in on this one. And then here, you would have to go out, but there's no edge that's not untraveled, so you can't do that. Unless, of course, this is the end, but even if this were the end, then there's the other problem is that you couldn't, the contradiction there is that you couldn't have come in first, right? You had to have left. There had to be some other edge that you left. Okay. So, all right, so here's K3. And so why am I showing you K3? It's a triangle. K3 is the complete graph on three vertices. So what is a complete graph? What is Kn? Kn is basically equal to, in terms of the vertices, it's V1 up to Vn, right? So there's n vertices. And then what are the edges? The edges are the set of pairs Vi, Vj, where I is not equal to j. So any pair any pair that is not just vi is exactly that. So in this case, we have this edge here, which is the edge v1, v3. We have this edge, v1, v2. And we have this edge, v2, v3. Keep getting messages, but I don't understand. Whoa. Holy crap. That's where all this crap is going. Okay. All right. Oh, I mean, I just did that out of like convention. Technically, if this is a two-directional graph, the edge v3, v1 is this. You can consider that to be the same thing, right? Maybe you call these like unordered pairs. If this is an undirected graph. Now, of course, if it's a directed graph, then you have an arrow pointing this way, and an arrow pointing this way, an arrow pointing this way, and an arrow pointing this way, an arrow pointing this way, and an arrow pointing this way. So it's either, I mean, so I'm going to stick with the convention that we have 3 edges here. But, yeah, who cares? All right, let's look at K4. Here's K4. So K4 is pretty cool. So the second set contains Vi and Vj. Well, the edge set contains Vi basically goes to Vj for every pair. But the first set contains V1, V2, V3. Yeah, so this is the set of vertices. And this is the set of edges, right? And edges are pairs of vertices. Is that true? I think that's true. Yeah. Cool. Yeah, so basically here's K4. K4 is the set of 4 vertices, and you see that there are edges from every node. Say 1 goes to 2, goes to 3, goes to 4. 2 goes to 1, 3, 4. 3 goes to 1, 4, 2. 4 goes to 1, 2, 3, right? So each one is connected. Yeah, I mean, if you're in an undirected graph, and I get the joke, Kevin. I'm not. Believe me, I'm with it. So basically, each node touches every other node. Yes. So this is like the definition of a K4. So these are not. Basically, these are not like. What should we say? Not all graphs are complete. And the vast majority of graphs are not complete. Like if you just draw some graph with 4 nodes, here's an example of a graph with 4 nodes. This is nowhere near K4, right? Because it's missing a whole ton of edges. On the other hand, it is a graph with 4 nodes. So I just want to talk about, KNs. Okay, let us see here. So let's draw out K5. So 1, 2, 3, 4, 5. And I'm going to use slightly smaller, and let's use green. Yeah, K stands for complete. Well, that's a good question. My guess, well, so incidentally, why do we call the integers z? And the answer is because in German, the word for numbers is Zahlen, right? And Yeah, and so in German, it's komplett, or whatever, complete. And so I think that's probably where it comes from. I mean, you know, in the 1800s, there were a lot of German mathematicians who did a lot of stuff. So they got to impose their, you know, Germanness onto the language of math. Wow, it's really hard to draw straight lines. But, well, if German is the best language, then yeah. Okay, so this is a K5. Yeah, cool. So here is, and then let's just draw out. Yeah, I could use the line feature, but you see, I didn't do that. So what does that say? And here's K8. I must have written in a comment. It's pretty cool, right? And so you notice that actually there's something that I was showing you guys. It was one of the what should I call it? So I think E8, this picture. Let's see. No. So, never mind. I was hoping that this was the complete graph on some number of vertices, but it is actually not. A Lie group is a group with a differential structure. I shouldn't say any of those things. Yeah, I mean, yeah, I don't want to talk about Lie groups. I mean, I'd like to talk about Lie groups, but I don't want to talk about Lie groups. So let's see what the next thing is. Here's a fun thing. How many edges does the Kn graph have? So let's do some counting. So K3 has 3 edges. K4 has 1, 2, 3, 4, 5, 6 edges. All right, let's count K5. 1, 2, 3, 4, 5, and then 1, 2, 3, 4. I think I've already counted that one. 5, right? Yes. It is a lot like that. So why is it that? Or very close to it. So someone says something like, and I'm ignoring the one term that you added on there because I don't like it, but this is very close. And so if we think about it this way, how many ways, if I have, say, n things in a bucket, right? How many ways can I pick 2 of them? And so the answer is, well, does order matter? Right? The answer is another question, and the answer to that question is no, it doesn't matter. And let me tell you why it doesn't matter. Because if I pick out Vi, Vj, or if I pick out basically like vertex 2, vertex 7, that's the same thing as picking out vertex 7, vertex 2, because we are using undirected edges, right? The undirected right. So basically, actually, the answer, the question is like, what is the number of edges in a Kn graph? And the answer is a really beautiful, simple answer, it's actually n choose 2, right? Because out of a set of n things, you pick 2 of them. And so the question is, what is that? Well, that's equal to n times n minus 1, but the only distinction is you got to divide by 2. And so that's kind of a fun thing, I think, because that's some like counting stuff that you can directly apply right into graph theory, right? I mean, we've just proven essentially that, well, yeah, so the difference between a directed and an undirected edge is that if you have a graph like this, remember, if we drew a bunch of dots and I say, let's say you can go there, you can go there, that is a nothing, so let's delete that. You can go here, let's say you can go back, but then you can go here, you can go here, you can go here, you can go here, you can go here. So, yeah, in a directed graph, order matters because the edge starting at Vi and going to Vj is different than the edge starting at Vj and going back to Vi, right? So if you notice, like some of these edges are 2-directional, and most of them are 1-directional. So like this edge here is 2-directional. And the reason why this edge is 2-directional is because you can go from this dot to this dot, but then you can also go back from this dot to this dot. But but here, for instance, if you started at this dot, you're only allowed to go this way or this way, but you can never come back because there's no edges leading back into the center dot. So generally, I'm talking about undirected graphs. If I talk about a directed graph, then, well, I mean, so I don't think I'm going to do it for the rest of the day, just because all the like interesting set theory problems are, yeah, basically it's like walking through a particular route where I guess it's more like it's on purpose. I don't understand. Anyway, okay, so oh, I'm sorry. Let me check OBS and make sure. I have myself turned down. It shouldn't be too loud. Oh, I was moving it against the table. Sorry. Should I talk about bipartite graphs? I don't know. He kind of vanished. He said he was going to join, but then he... Oh my good God. So, yeah, I guess so. So, okay, so here's a fun little fact. I don't know that we're really going to talk about bipartite graphs that much. I just, I threw it in here because it's kind of an interesting type of a graph. So a bipartite graph is a graph where there's 2 sets of vertices. So you see here, I guess, in this case, this is like V1 and this is like V2. Or you can call them U and V whichever naming convention you like. And so I just stole this picture. And so basically the idea here is that you're only allowed, it's a directed graph. Actually, it could be an undirected graph. So it could be either directed or undirected. But the rule is that you can only have edges from V, like the set V1 into the set V2 or back. And of course, if this is an undirected graph, then actually that's equivalent to saying an edge can only go from V1 to V2 because then you have the reverse edge. So So here's a fun little theorem. We're not going to prove it, but I think it's kind of an interesting fact about bipartite graphs. Yeah, it is a lot like that, yes. And of course, in this case, you can assign multiple things to multiple things. So everything can, and you notice this one doesn't have any friends in the other graph, but like this one has, well, I guess you could say which one has multiple friends. I guess 2 has multiple things coming in. None of them have multiple things going out. Interesting. But that's not a rule or anything. You could have like an edge going out literally to every. But here's the fun fact. The fun fact about it is that a graph is bipartite if and only if it contains no odd cycle. So that's an interesting... I think that's interesting because it kind of makes sense. So here's why it makes sense that a graph is, if it has, or let's put it this way. If a graph is bipartite, it should have no odd cycle. So what is an odd cycle? Basically, an odd cycle is something where you can go around in a loop. So 1, 2, and then let's say that we can go here, 3, 4, 5, and then let's say that you can go back 6. So you see that was a cycle. That's a cycle because it's a set of edges where you start at a place and you get back to that place, right? It's the same thing as calling it a circuit. So basically a cycle So an odd cycle is just a cycle of odd length. And so basically the idea here is that if you have some bipartite graph, right, you have some set of nodes here, it's impossible if I do something like this, and then I go over here, and then I go up here, and then I go back. We count the number of times we had to, the word is circuit. Maybe I'll just erase it and type it. Because I know that I called, we were talking about like Eulerian circuits, and here it says cycle. What's the difference? There is no difference. It's just a standard thing. Okay. So basically, if you have a bipartite graph, like if we say that this is a bipartite graph here, like this is the set V1, and we set that this is the set V2, the only rule is that this edge here is not allowed to exist, and this edge here is not allowed to exist, right? You can't have these dotted edges. The reason why is because if it did exist, then it wouldn't be bipartite anymore. So the idea here is that all the cycles, all the paths around a bipartite graph, if you have, say, 3 nodes, right? So this would be 1, 2, 3, 4, 5, 6 edges. So basically, all of the the theorem says that if there's an odd cycle in the graph, meaning if there's some odd way to get around, then what that means is that there had to have been some like edge that connected here. That's essentially what the proof would have been, right? So you would have said, assume that there's a bipartite graph and assume that I have some odd cycle. And then what you would have done was you break it down until eventually you kind of prove that there has to be some connection between 2 elements of the same like half of the bipartite set. And that way you basically would show a contradiction. And so then you would prove the one direction of the fact. The other direction of the fact is actually interesting as well, because you can always say that a graph is bipartite if and only if it contains, so the only if part. So it doesn't just mean that if a graph is bipartite, it contains no odd cycle. It actually means that if a graph contains no odd cycle, so you just have some random graph, right, that contains no odd cycle. Kn graphs contain all kinds of cycles, right? Like if I have K4 here, let me just show you K4. So here's K4. I can make an odd cycle this way. I can go this way, and back. The arrow between 8 and 3 is going from 8 to 3. Yes. But nothing's really dependent on that, right? It's not like vital that it's just an example. We're not actually using this graph necessarily. Yeah, so you can only make, so yeah, that's what they mean by cycle. So they mean you have to go around in a circuit. So basically if you start here and you go here, 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 that's a 4-step cycle, but that's not what the theorem says, right? It doesn't say that there aren't even cycles. It says that there aren't odd cycles. And here we have like a cycle where we can go around like this. We can say start here, go, 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 right? And that's an odd cycle because there's 3 edges. So it's an odd cycle. The red cycle, I guess I'll draw, right? If you go around this way, that's an even cycle, but who cares? Because it doesn't, like the existence of an even cycle doesn't really tell you anything. Let's see here. If there's an area, yeah. So if there was an arrow that was going from here to here, this would break the graph, right? It wouldn't break the graph, but it would break bipartiteness. Oh man, it's really not writing. Okay. Okay. No, bipartite this is the definition, right? You can go only between, I don't know what that means. Bipartite just means that there's 2 collections of nodes where you can only go between the first set and the second set, or the second set to the first set. You cannot go, no edge exists inside of the first set of vertices, and no edge exists in the second set of vertices. Yeah, I'm not sure if that has a name. So there's something called the utility graph. I think it has some other names, but this is one of its names. And it's a bipartite graph. 1, 2, 3, 4, 5, 6. So I'm actually dividing it up this way. It depends. Yeah, probably. So here's the utility graph. And let me see. Do I need more? I think I might need this one, and I need this one. Yeah, so a bipartite graph cannot have a shortcut within its own set. So you see here, this is basically our V1 set, and this is our V2 set. Okay. So there's another name for this graph, as awful as you might think. It's called K33, which actually means that it's a bipartite complete graph, or like a complete bipartite graph or something. Which is slightly different than being a complete graph, because in a complete graph you have to have every vertex connected directly, right? There needs to be an edge. There would have to be like a red edge here for this to be complete, or a red edge here, or a red edge here, or a red edge here, and actually also these to make this a fully complete graph. But so this one is not actually, so it's not complete. But it's like a slightly less good form of complete. And so there's actually an interesting fact in graph theory. Let me see if we can get to it. Where is... not this one. So here is the fun fact about the universe that... So first let's talk about what a planar graph is. So a planar graph is something that can be drawn on 2 dimensions without having anything cross. So for instance, this is a planar graph, but this is not a planar graph as drawn, right? Because of this crossing here. So, and we notice that most of the complete graphs don't really have much of a chance of being planar. And the reason is, like, if you look at all of these I shouldn't call them vertices. If you look at all of these intersections here, none of these are vertices, right? So if these were all vertices, then this might be a planar graph. But because none of these are vertices, this is a hugely non-planar graph, because you can't draw it without intersecting all these edges over and over. Even if you tried some like tricky stuff, like instead of drawing this edge here, if you like tried to get around here, and you did this with all the edges like that, you could do this, you could do that, you could do this, and that would get rid of some of these. But as it turns out, you can't get rid of all of them. There's still all these other connections, and if you tried to do the same trick, then the problem is, even once you leave this, you still have to get to 2. So the problem is, if you tried to do something like that, you would still have to cross around and get here. So can you draw a Kn as a planar graph? The answer is sometimes. So you can draw a K4 as a planar graph. Here's a K4 that's planar. So this is okay. And then there's only one... Yeah, if you make bridges and tunnels, then yeah, that'd be nice. Here's the trick to make it planar. And you shouldn't use the arrow, let's get rid of that arrow. It's an undirected graph. So this makes K4 planar. This is a K4 on the plane. Okay. But now, of course, you knew there had to be a but somewhere in this, right? K5 cannot be done. It's Mountain Dew. So if you draw 5 points, and we draw K5, So if we draw K5, yeah, it should be. So, I mean, I could always give this as a trick extra credit problem, but I would never do that to you guys. The whole point here is that if I'm not going to prove it because A, I'm not sure exactly how I'd go about that because it's been a while, but also B, I think the right way to do it is to kind of convince yourself that you can't do it through standard tricks, right? You can be like, well, okay, I'll just remove this edge then, and what I'll do is I'll redraw it up here. So let's see if we can make a K5 that doesn't cross. But we still have these three things, so let's pull this one out here. And so, okay, there we go. That one gets pulled out. And now we have one problem left, right? So this is not a proof, right? This is not a proof, but this is kind of evidence, right? Let's call this evidence that it can't be done. Because you see that there's a lot of symmetry here. So whatever I'm doing, if it worked in one direction, it'd have to work in the other direction. And now what you see is you have to get this node, right? This guy has to connect to this guy, right? But it can't cross through here. So, okay, so it can't go into this region, but it can't go into this region. Otherwise, it'll cross either through here or here. But it can't go through into this region, right? And it can't, so like that's the problem here is that if you took out this edge, or maybe I'll just like recolor this edge blue. What we see is that if we took this edge out and we tried to feed it in through here, there's nowhere to go. If we tried to get out this way, there's nowhere to go. And we already tried to get out this way, there's nowhere to go, right? Because we crossed through here. We're not allowed to. That's right. A planar graph is a graph that can be drawn without any crossings on flat paper. So, like, you can basically draw any graph on paper, but you're going to get, as you see, like in K8, you're going to get just a ton of crossings for some of the graphs. Okay. So K5 can't be done. As it turns out, this utility graph, this K33 thing, also can't be done. So this graph, as you see, has a ton of self-intersections in its edges. And so I'm going to say that as drawn, it's not planar. But that actually doesn't show that a graph is really not planar, because I could draw a graph like this. I could say, here's a graph, and here's an edge, and I could just do this. And you would say, but you didn't need to do that, right? You could have moved this node up and around, or you could have just moved the edge around, or done, right? So like if you have a graph and say we have this, we could have done this, or alternatively, we could just move the edge and do that, right? So this graph is actually a planar graph. It's just not drawn that way, right? So it's always possible to draw a planar graph with a self-intersection. The question of being a planar graph is not, are all the drawings not intersecting? Because you can always kind of make one up. It's, does there exist a good one, right? Does there exist a drawing of the graph that doesn't intersect? And you see here, we have essentially, I mean, really this is just the same drawing, because you can just, it doesn't matter whether this, you can just push this node wherever you want as long as it's not crossing through any of these boundaries. So that's kind of the point here. Yeah, so anyway, what else should I say? So yeah, I want to say that a K33, this thing, is not planar. So, it's a challenge. What you should do is you should play around with it until you convince yourself there's really no way to do it. Because if you start trying to do the loop-de-loop tricks, right? So let's draw some of this stuff. So we get like this, this, and we'll get this and this. And then after that, yeah, so I mean, my point here is not to really test you on almost any of this. I just want you guys to like be interested in math, and like this is actually math. It's also computer science, if you're a theoretical computer scientist. So this is like the boundary of math and computer science. And so this is actually, I think, some really cool stuff. So like if you wanted to connect these things, you know you can't go through here. So I'm just going to go around, and I'm going to make this weird heart thing, or whatever it is. Hopefully it doesn't make anything obscene. And then let's think, what else does this have to connect, right? So this connects all of this stuff. This guy has to connect all the way out to here. But you see that the current drawing makes that impossible. Yeah, the traveling salesman problem is definitely a graph theory problem. And so you see here that, now this does not show completely that K33 is not a planar graph, but it shows that the tricks that I've been trying to tell you guys to use, like, oh, let's shift this node around here, let's do this around here, like, so actually, there's one more trick we have, or I guess we can connect this guy down to here, and we can connect, oh wait, yep, we can do that. But then, we still have to connect this guy to this guy. There's a bunch of problems, right? So, like, we have to connect this one to this one. We also have to connect, for instance, oh, this one and this one are connected, but we have to connect, what else do we have to connect? This is connected to all the things in this graph. Is that the only problem? This has 3. 1, 1, 2, 3. 1, so 1, 2, 3, 1, 2, 3. Oh, this one has, yeah, so that has to connect to that. And 1, 2, 3. So actually, we got pretty close. This is as close as you can get. All of them are connected to the right nodes to make the utility graph, except for the 2 blue ones. And as you see, like, there's just no way to get at this dude, right? Because if you try, you would say to yourself, okay, well, I'll try to wiggle myself around this way. Oh, wait, there's this boundary here, so I can't go in this way. So that means I have to go in this way. But there's no way to get inside of here. So maybe you remove this, but then if you remove this, then you have to do other things. So that's the point. So there's just a lot of, like, going around in circles on this. Yeah, I really don't even want to get into, like, the technicalities of the proofs of these kinds of things. I just think it's cool that like, you can basically argue with yourself. This is essentially what the proof should boil down to, right? You have this guy here who's connected to this guy here, but they're just not quite jiving. Yep, okay. So, as it turns out, that's all you need. Let me see if I can find it. Yeah. So this corollary is kind of the important one. This is like a very famous theorem in theorem, corollary, whatever. It's either a theorem or it's a... So a planar graph has at most 3n minus 6 edges. So this lemma kind of helps us out quite a bit. So if we look at the K5, and we say K5 has 3, well, so what is 3 times 5 minus 6? Is equal to 15 minus 6, is equal to 9 edges that it's allowed to have if it's planar. But K5 has 10 edges. Huh. And so that's a contradiction, right? So K5, this is actually the proof that K5 cannot be planar. is if you believe this lemma, which there's no reason for you to believe it yet, but basically the idea here is that if you believe this lemma that says that a planar graph has at most 3n minus 6 edges, then you just calculate the number of edges that K5 has, which is 10. We know that from earlier. You calculate 3 times 5 minus 6, which is just n is the number of nodes, and we're good. So what about the utility graph? The utility graph is, so it can have as most 3 times 6 minus 6 edges. And it has, how many edges does the thing have? I'm not sure that this is actually the right proof that gets you there, but so that'd be 18. So it would have to have 12 or fewer edges for the utility. And so the question is, does it? And the answer is, why don't we just look at a prettier version of the utility graph? Yeah, here we are. So how many edges does it have? It has 1, 2, 3, 4, 5, 6, 7, 8, 9. So, oh yeah, oh, incidentally, if you ever see the name Hamilton in mathematics, it's probably William Rowan Hamilton, who's an Irishman. So it's not me, obviously. I think William Rowan Hamilton has his name on the thing called the Hamiltonian too. Let's see, William Rowan? Yeah. I don't believe that I am, though I could be. I don't really know all the details. But yeah, if you've heard of the Hamiltonian in quantum mechanics, then that's also named after him. So the utility graph is a non-planar graph. But this fact does not get us there for K33, because K33 only has, I guess, 12 edges. And so, I'm sorry, K33 has, what? It has exactly, or am I wrong? It has, no, I think it has like 11 edges, right? Because this thing has 1, 2, 3, 4, 5, 6, 7, 8. Oh, it only has 9 edges. Yeah, my counting earlier was right. So it only has 9 edges. So actually 9 is less than 12. So this theorem doesn't really show any problems, so that's okay. My guess is that let's check the Euler characteristic. So this is something called the Euler characteristic of a graph. And so the Euler characteristic is when you add up the number of, basically it's the nodes minus the edges plus the faces. 9 is less than 12. I'm pretty sure of that. I don't know all the details, but I'm pretty sure that 9 is less than 12. So it's okay. So it's not a contradiction because it just says that a planar graph has at most this number of edges. It doesn't say that all non-planar graphs must have more, right? It just says, you know, if it's planar, then it has this number of edges. So there's a fact that a connected plane graph with this has this. So how many nodes, edges, and vertices does a utility graph have? It has, well, 1, 2, 3, 4, 5, 6 nodes. It has 9 edges. Oh god, and then how many faces? That's a good question. Check the piano axioms? Yeah. So, anyway, I just wanted to get to the cool theorem by the end of today, which I think I'm basically there, that if you have a graph, and inside of the graph, you have a K5 or a K33, then that graph is not planar. So that's actually some pretty cool stuff. All right. Yeah, I think that should be it for the day. Maybe, yeah, K33 is the utility graph, right? That's the thing that I was drawing. That's, and I should put a little asterisk on this when I say contain. There is a specific meaning of contain, meaning that you're allowed to basically contract edges. So if I make a graph like this, the containment allows you to actually, so I'm allowed to look at these edges and be like, okay, I can collapse all of this down into one thing. And by one thing, I mean like I just kind of make the vertices the same. So then you would have like just one vertex in this. A utility graph is a non-planar graph. Yes, it is definitely non-planar, because if a planar graph cannot contain a K33, then K33 contains itself, and so it can't be planar. So I think this is like one of the most interesting, kind of like almost accessible parts of mathematics that, you know, you don't need the kind of background. You don't need to know about. Well, I accidentally let the tablet fall. So yes, I guess I am slamming my desk. Yeah, so it's one of the most interesting kind of like accessible pieces of mathematics that doesn't require a gigantic amount of background to like understand. Sorry about that. Yeah, boom, end of lecture. So, yeah, there's some other stuff that, if you're ever interested, I think next time I'm going to I've already discussed big O in 201, so I don't feel like talking about it anymore today. But I'm probably going to tell you guys a little bit about big O and big omega next time, and then on Monday we'll do review for the final. And by review, I mean I'll probably just go over the practice final that hopefully I will write. Yeah, so... But if you're ever interested, there's some really cool stuff in Ramsey theory that I honestly never had the time to learn myself, but I would really like to have the time. And if I ever get the time, then I will definitely learn more about it. Can I post these slides? Sure. Yeah, I'll post them. Yeah, I'm not entirely sure what I'll do for graph theory in terms of a question. Whatever the question is about graph theory, it's going to be, maybe I think, you know, one option is that it can be simple. And what I mean by simple is like, I'll say, draw a graph of a specific kind, right? That would be a good extra credit question. I don't think that the question should be of the form like, prove that all graphs of this type have this property. That's probably pretty far beyond the scope of this course. So I don't want to force you guys into something horrible like that. Yeah, so basically, like the extra credit question, I think is just going to be like a drawing question. So I'll try to come up with like a practice one so you can get some practice on the practice final, and then yeah, we'll just have it on the final is like a 5-point extra credit or something like that. I'll think about what I'm doing. It's, you know, who knows. All right. Well, I think I'm going to end the lecture now. I guess Ben never actually joined in, but that's okay. I'm sure he'll join in next time. All right. I'll let you guys go. Have a good rest of your day.